So my little Calc 2 babies, I know that you woke up today thinking, I really need more puzzles in my life. I've just gotten bored with the current amount of puzzles that I have, and I'm missing something. And good news, you've come to the right place. So where are we? Well, we're in Chapter 8, the third section of Chapter 8, which is what we call trigonometric integrals. And we are going to play a game, okay? And there's some, just like any game, you could always look up tips and tricks on how to get better at the game to make life easier. And we're going to kind of go through some of those tips and tricks. But the idea, let's not lose sight. The idea is you simply want to be able to find some new ways of integrating. And in this case, we're going to have integrals that involve multiple parts of, or multiple trigonometric functions. So, but let me start. Let me start with something. Let me start with the question of how might you integrate cosine to the fourth of x with respect to x. Now I've asked this question and I'm going to punt on this question. And you'll see why. And let's just say I ask a new question. How would you integrate the following? Well, the good news, the second question is a lot easier to integrate. We have been down this path before. So for the sake of time, let's just go ahead and finish this. We can split all of this up into the sum of three integrals. And if we do, it would look something like this. We would have 3/8, which we would integrate. Notice I'm bringing that 3/8 out front of the integral. And to that, I would want to integrate. I'm going to bring that 1/2 out of the integral. And then I'm also going to want to take 1/8 and bring that out in front of the integral. And don't let me forget my dx's. I have to attach my dx's along the way. And okay, so at this stage, all I've done is taken my integrand, broke it up into the sum of three different integrals. And just for the sake of time, I took any constants of multiplication and brought it out front of the integral. Now, let's go ahead and start this integration process. So if you integrate, right, if you integrate 1 with respect to x, you simply get x. Of course, we have a 3/8 attached to that x. All right, now plus, I'm going to go ahead and write, we have a 1/2 attached here. And now let's think about how we would integrate cosine of 2x. Well, hopefully you're already thinking that's just simple u substitution. We let u be 2x, du would be 2 dx. And this should be old hat for everyone in this class. I have the dx, but I do not have the 2. But let's make sense of that. I think you would allow me to place a 2 here so that 2 dx can become du. If I'm willing to also compensate for that doubling by halving. All right. So in that case, we can go right through, do all of our u substitution, and we end up with 1/2 times 1/2. And I'm going to do this quickly. This should be easy for you. If you now integrate cosine of u with respect to u, then back substitute the 2x back in. we end up with sine of 2x. The same applies here, except now u is 4x, du is 4 dx, which requires me to multiply by 4 here and compensate by multiplying by 1/4 here. Plus, that would be 1 over 32, and the game is the same. We now can just simply integrate cosine of u with respect to u, which gives us, and back substitute for x, which gives us sine of 4x plus c. All right, so all I'm going to do is clean this half times a half, write that as 1/4. And voila. Okay, now what does this second question have to do with this first question, right? Because I initially asked, how would you integrate cosine to the power 4 with respect to x? And then I immediately punted on that question and went to an integral that we actually do know how to do. But now here's the little secret. You actually can rewrite cosine to the power 4 as this 3/8 plus half of cosine of 2x plus 1/8 cosine 4x. But how do you do that, right? Well, you would have had to have been paying attention back in your trigonometry class. Maybe that was in pre-calculus part 2. But it's just making use of some identities that that you worked with back in your trig class, right? So just making use of some power reducing formulas, which can be derived from the double angle formulas, and then the half angle formulas. These at the time, they were just these random identities that you were dealing with in your trigonometry class. You probably never were quite sold on the idea of why these would be important, and am not going to even take the time to try to sell you on that idea right now. The more important thing is to know is that in mathematics, the highest form of equality that you can be given, the highest form of the label that you can be given in terms of equality is to be identical, right? To be an identity. Other forms of equality are conditional equalities. So for example, if you solve the equation 3x is equal to 3 and you tell me x is equal to 1, that's a conditional equality. It is equal, the equation is equal under the condition that x is 1. With an identity, so for example, 3x is equal to 3x, that is identical or true for all x, right? That's what we mean by an identity. And now what's beautiful is if my work here is legible, what I'm doing is I'm just applying a power reducing formula, right? A half angle formula for cosine squared over and over and over again, and I'm just reducing and reducing and reducing and reducing and reducing until we get down here to the bottom. And have you seen that before? 3/8 plus 1/2 cosine of 2x? Well, I think you have, because that was what we had here, right? So when you're working inside of integrals, you don't you want to be able to manipulate without dealing with the properties of equality, right? So notice that what we do is we take cosine to the power 4. And it's not like we're adding to both sides of the equation, multiplying both sides of the equation. We're not dealing with these properties of equality. We are simply taking cosine to the power 4, which we can rethink of as cosine squared. And it just so happens that you have a formula dealing of how to rewrite cosine squared. So 1 plus cosine of 2x over 2. And that's what I'm doing. You can follow this work on your own time. Now, that's interesting, but that's not really the topic of what we're going to do today, but it is similar. It is similar. So what we're going to do is we're going to come up with some strategies, and I'm going to be flipping back and forth. I'm going to show you that right now. We're going to have some tips, some strategies for dealing with various integrals of sines, cosines, secants, tangents, etc. And I'm going to come back and refer back to this page multiple times. Okay, but first let's actually jump into a question that we want to be able to answer. So notice example 1. It says, can you integrate sine cubed of x multiplied by cosine to the 4th of x with respect to x? Right, so this little graph that I have produced for you here was in no way part of the example. It's not required that we know what the graphs looks like. But for me, I studied applied mathematics, but my what you've probably heard me say on multiple times is I either need to see the geometry or I need to see it in an application. Otherwise, it just doesn't stick. I might be able to follow the recipe, but it's not going to stick. So I produced the graph of sine cubed cosine to the 4th, which is just, remember, you integrate derivatives. So this is just the graph of some derivative, and that we are trying to integrate our way back to the function, the original function, right? Or it obviously won't be the exact function. We'll have plus c along the way. Speaking of which, I did put plus c in my previous problem, did I not? I did. There it is. It's funny when I start to second guess myself. So I always like, before I tell you not to do something, to make sure I just didn't don't forget your plus c. I want to make sure I didn't on the previous page forget my plus c. Now, so what's some strategies? Well, in this particular example, let's notice the powers of sine. Okay, and so in this case, we're looking at sine cubed of x, and the power is, well, obviously it's 3, which is odd as well as positive, right? So it would be nice to, I don't particularly like to do math this way, where I just follow recipes. You would be much better off if you jumped into this problem and started playing. Right, you just decided to choose a u like cosine, and then see what happens. What did I just do to my cosine? Right, and then just see where it leads you. But for the sake of time here, I mean, obviously we don't have a long time to go through this. Let me kind of show you at least let me offer some suggestions. So notice that what they're saying here is, when you're dealing with sines and cosines in your integrand, and that is what we have in example 1, we have a sine cubed to cosine to the 4th, you have some choices, and the choices are basically are dependent on whether your sine, the powers of sine are odd or even or positive or negative or things like this. And what this first little tip is suggesting is, look, if the power of sine is odd and positive, then what we're going to do is we're going to want to save a factor. So you got to listen to me right now, right? You got to listen to me. The goal is you're going to use u substitution, right? In this case, we are, in that previous example, we are going to let u be cosine of x. But immediately look at the consequence of if we let u be cosine of x, that means du is negative sine of x dx. That means I have to save a factor, right? Like, let's think of this as a puzzle, and I need to save a piece of my puzzle for later in the problem, because I have to, in order to convert to du, I'm going to have a sine of x dx laying around. The negative doesn't really matter, but the sine of x dx is what matters. So the goal is, and let me see if I can capture that tip that was on the previous page. We are going to, so here's my, let me write this here. So my tip is to save one factor of sine of x. So save a factor of sine of x for the du, right? So I got to save me a sine of x. We're going to pick a sine of x and keep it for later. And then we're going to end up turning everything else into cosines. Right, so we're going to use these identities that we have access to turn everything else into cosines after we save one sign. Ready? No more talking. Let's jump in. So the first thing I'm going to do is I'm going to rewrite this integral, right? And what I'm going to do is, I'm going to save me. So I had sine cubed. Look what I'm doing right now. There's a sine squared. And you're thinking, whoa, hold on for a second, Professor. You forgot it's not sine squared. You're thinking it's sine cubed. Yes, I know. And here is this other sine that I was talking about saving. Right? So take a second and take that in. I took sine cubed and rewrote it. Right? I rewrote it as sine squared times sine. All right, that's what I mean by this tip right here, to save a sine of x for du. Ready? And now let's go ahead and follow our recipe. So we're going to let u be cosine of x. And as we've already seen, the consequence of letting u be cosine of x is the fact that du will equal negative sine of x dx. All right. So I'm going to, at this stage of this problem, I'm going to leave that cosine alone. All I'm going to do is plug u, my apologies here. I'm going to let u, think about plugging in u for cosine. All right. So let me do this. I hate when I change my strategies along the way, but let's do it this way. I think this, so let's go ahead and go to tip 2, right, which is turn all else into cosines. I mean, look right here. I'm I've done my job. There's my sine of x dx. I have it in green. I'm not going to forget about it. I'm going to leave it there. What I'm looking at is what's left here. It says turn all else into cosines. So now my question to you is, how do I turn sine squared into cosines? Well, sine squared, if you recall your Pythagorean identities, right, which is just right up here, sine squared is 1 minus cosine squared. All right, so sine squared is just 1 minus cosine squared. So what's going to happen is, as of right now, I'm going to rewrite this sine squared as 1 minus cosine squared. Let's go ahead and do that. So now I'm integrating 1 minus cosine squared I still have my cosine to the power of 4, and I'm going to use a different color because I'm not going to forget about this sine of x dx. I got to use that guy later. All right, so tip 1, factor out a sine of x and save it. Good. Tip 2, turn all else into cosines. Done. Ready? So now let's just distribute. All right, let's try to make our work a little bit easier here. So now I have the integral of cosine to the power of 4 minus, well, cosine squared times cosine to the 4th is cosine to the 6th. And again, here's that sine of x dx that I've left alone for the time being. All right, now what I'm going to do at this stage is split this up into 2 different integrals. So if you think about it, I can distribute that sign to both. That part doesn't really matter. But what matters is what I'm going to do right now is go ahead and split this up. So now I would be integrating the cosine to the 4th of x. Now, don't let me forget my sign. I gotta have a sign there. All right, and now that would be minus, and I'm gonna remember I'm splitting it up into 2 integrals. Minus cosine of 6x, and don't let me forget I still got my sine of x dx. That looks horrible, but I can't do anything about that. Try one more time. Okay. And now we're going to go ahead and use that u substitution, right? We've already defined it up here. So follow me. So now anything that has a cosine of x is henceforth referred to as u. Right, so at this stage, u is cosine, du is negative sine dx. All right. So ready? Let's do this. So now we're going to have the integral of u to the power of 4, right? Because cosine to the power of 4 is now just u to the power of 4. And hold on for a second. I can't just convert yet, right? I can't convert sine of x dx into du because I need negative sine of x dx. So you know what happens. I would have to have a negative here in order to make that substitution, and in order to compensate for that, I'd have to put a negative out here. So it's going to be a negative, or out in front of the integral. So negative u to the 4th du. All right, and let me see what's going to happen here. So I know I'm going to leave the sign out for just a second. I know that that's going to be u to the 6th because I had cosine to the power of 6. And just like I did prior, I'm going to have a negative here, which brings out a negative out here. So does everyone at this stage right now, do you see that this double negative is going to have to turn into a positive? And that allows me to just simply substitute du. All right, now at this stage, we integrate, we back substitute. Let's go ahead and get to our answer. So the answer in this case is going to be negative cosine, well, that's u to the fourth. Integrated would be u to the fifth over 5. So that's cosine to the power of 5x over 5 plus cosine to the 7th x over 7 plus c. All right, and let's stop for just a second. So if you like puzzles, if you like puzzles, you might just dig integration in general. If you're not the type of person that likes puzzles, well, this might be quite annoying to you, right? There's all these little things to remember if your powers are odd or positive, and I get that. That's why I said I don't like to do math this way. I think that you are much better off jumping in when I say jumping in, I don't mean to jump in on your test, right? I mean jump in when you have the stakes are low, like when you're doing your homework. Jump in and start to play, because if you let u be cosine of x enough, you're going to know that I'm going to need to have a sine of x left over to do this substitution. So let's go to another problem. All right, so example 2. Now, in this case, let's take a look at our, actually, in this particular case, let's look at our cosine, right? So in the previous one, we looked at our sine, and now what we're noticing is the powers of cosine are odd and positive. And the strategies, again, which is on that previous page, this is in your textbook as well, I believe. But the strategies that are on that previous page say, look, if you have powers of cosine that are odd and positive, then you're going to want to save one of your cosines for your du. But you're going to turn the rest into sines. Right? Very similar to example 1. Only now we're going to let u be sine of x, and immediately du is cosine of x dx, right? So this is what we mean by, look, save a cosine for a later. So let's go ahead, let's jump in. I'm gonna take this integral. I'm not worried about the upper and lower bounds. Okay, I'm not worried about doing the definite integration. I'm more concerned about learning the technique, the way it sits of this new trigonometric integrals. So let's go ahead and let's start by rewriting, okay? So let me follow my advice. So I said I want to save a cosine for later. So I'm going to rewrite this as cosine squared times cosine of x, right? I'll tell you what, I'll write this in a different color. Here's what I'm going to save for later, for my du. And of course I can, right now I'm just trying to make my life easier, if I can. So I can rewrite this as the square root of sine of x as sine of x to the power of 1/2. And hopefully you can anticipate where I'm going to go next. So let's go ahead and continue. So to divide by sine to the power of 1/2 is to multiply by sine to the power of negative 1/2. Okay? So let's go ahead and rewrite this as, well, actually, I tell you, before I even do that, let me go ahead and continue in my tips. Let me turn everything else into sines, right? I don't mean to change midway through the problem. I am going to do what I just said I was going to do. So this is sine of x to the power of 1/2. Just I'm trying to follow my tips. So right now tip 1 is done. I have saved a cosine. But tip 2 says, the second tip asks us to turn the rest into sines. So in other words, I want to turn this cosine squared right here. I want to turn this into sine. All right, well, where do I want to write? So obviously, cosine squared, again, this is just a Pythagorean identity, is just 1 minus sine squared. So now I have 1 minus sine squared and I'm going to multiply that by my cosine that I'm saving for a rainy day. Okay. All right. So now let's see what we can do here. Well, we can always split this fraction up, right? Let's see if you can follow me. Let me write and then I can elaborate. So I can split this fraction up. This is just the integral of 1 minus sine of x to the half minus sine squared x over sine x to the 1/2. And of course I still have my cosine of x. Right? You with me that all I did was just split that up. And I think you can probably see where I'm going to go with this. As I'm going to end up splitting this up into multiple integrals. I just need that to have a cosine left over, right? So that's the main thing. So let's see if we can simplify what we've written here. I hope this is legible on your end. So this would end up being integrating. Well, let's start with this. We got 1 over sine to the half, right? 1 over sine x to the half. That's just sine to the negative 1/2. So sine of x to the negative 1/2. All right. And I want to make sure I keep my cos. I'm going to go ahead and leave the cosine out front. And now that's going to be minus. And now let's see here. If I have sine squared of x divided by sine of a half, maybe I should write down here. So if I have sine squared of x over sine x to the 1/2. Well, maybe it would be easier for you, because we are just going to, when you divide like bases, you subtract the exponent. So maybe it would be easier if I wrote it like this, right? That's the same thing as having, let me not use a term that I've used in this problem. Let's say that this were m squared divided by m to the power of 1/2. Well, that's just m to the power of 2 minus 1/2, or m to the power of 3/2, right? So that is what I'm going to write, except instead of having an m, I'm going to have a sine. So this is sine of x to the power of positive 3/2. All right, and I still have my cosine and I still have my dx. Okay, so let me erase this work down here at the bottom. How's your energy levels doing? This is, I would imagine this is tough. I mean, when you're in a classroom, you're stuck with me, right? You don't have anywhere to go. You might be able to grab your phone and check and see what's happening in life. But man, you have it hard because let's say you're at your house where there is an infinite amount of distractions. And you got to be careful because you can trick yourself into thinking that you're studying when you're not, right? Like, you don't want to be busy. You want to be productive. So if you are if you find this easy, then maybe you can give it just a small piece of your, you can give it a small portion of your attention span. But please be careful. Don't trick yourself into thinking that you're playing a video game, listening to a song with your phone in front of you while this is playing in the background, and you're tricking yourself into thinking that you're actually studying right now, right? Because, again, you want to be productive with your time, not just be busy. So be careful. Now, at this stage of the game, we're ready to use our U substitution. And again, the whole point is, so since we're going to allow U to be defined as sine of x, which means du is defined as cosine of x dx, then let's go ahead and split our integral and U substitute. Ready? Let's go. So we're going to integrate sine to the power of negative 1/2 x. I still have, remember this cosine? It's been there for the ride, right? It's been just along the way, coming with us for this next step. Minus, now we have the integral of sine of x to the power of 3/2. And again, this cosine has just been along for the ride. All right, now, perfect time to U substitute. If you hear my family's watching me, clearly they're watching a comedy in the background because they're laughing like crazy. My two boys and my wife. So, but I'm here with you because I love you. Right? I'm here making videos for you. So that cosine x dx can become du. Right, and this would be u to the power of 3/2, and again, that becomes du. Okay, and let's get to the answer. From here, this is old hat. So you just use your power rule for integration, back substitute everything in, or we end up, remember you're adding 1, obviously, right? So what do we end up with? Well, we end up with sine of x. So if I add 1 to negative 1/2, I have to the positive 1/2 over 1/2 minus, if I have $1.50 and I add $1, then I have 5/2, right? $2.50. All right, so remember, along the way I said I was not worried about that definite integration. If you were going to do the definite integration, it's at this point you would do that f of b minus f of a, but I'm not worried about that right now. Okay, so let's kind of we're gonna take a break in this video, and I'm gonna pick back up in the rest of this section in another video. To recap, we started off with that example of trying to integrate cosine to the power of 4, and this is what we were what we did in that previous page. Like if you go back to, I think it was page 2, if you go back, and you'll be able to see how you can use some basic power rules to split up cosine, or you can try using some of these new techniques to split up a cosine. I'll let you do that on your own time. I wanted to show you something that's actually kind of cool. So notice that, so this right here, what I have boxed in, what I have circled, this is your integral for example 3. Right now, I'm going to just bring this down here. And we're going to assume for just a second, let's assume for just a second that the question is the same, but we wanted to integrate from 0 to pi over 2. Well, clearly we don't need that plus c. So the only difference, we would have the same result, but we would now have from 0 to pi over 2. Right, and this is actually this little trick is what's known as Wallace's formula, right? So Wallace was just another, I don't know if you would say he was a mathematician of antiquity, right? He's really just 1600s, but did some great work. He can, again, it's been quite a while, but I know that he definitely had a lot of influence on Newton, on Leibniz, so he had a lot of influence on the calculus. I think he was credited for the notation that we use for infinity. I think this was from John Wallace. So anyway, but this is John Wallace's formula. And notice what it says. It says, look, if you're trying to integrate a cosine. Now this does work for sine as well, right? It's also valid when cosine is replaced with sine. So if you were integrating a cosine to the power of 4 or to the power of 5 or to the power of 6, but you were integrating from 0 to pi over 2, notice something here, that we have a very quick way of actually just getting to the result without doing any calculus at all, right? It's just it's an astute observation. I'm not going to ask you to prove this, but it's an amazing observation, and it does have a proof as well. So which one of these cases is the one that we have? Well, we have case 2, right? If your cosine has an even power greater than or equal to 2, that's what we have. We have cosine to the power of 4. Then notice that we can just go right here, right? So bear with me. So that it's telling us that we can actually do no calculus at all. We can just say, so, well, what is n in this case, right, if you're awake? So it's cosine to the power of 4, so therefore n is equal to 4. And watch this. Quite amazing. If you just plug in 4 for n, we have 4 minus 1 over 4 multiplied by pi over 2, which is just 3 pi over 8. Now, since we're concluding here, you should try on your calculator, you should try running this integral right here, right? Because your calculator's robust enough to do this. Run this integral right here from 0 to pi over 2 and see if you don't get 3 pi over 8. So you could have gotten there. And the main reason is that this right here is the only thing that contributes to the solution, right? This, I'll box that in one more time in case you missed it. This 3/8 x is the only thing that actually contributes to the solution process. And that's why it works. So again, very cool observation. We're going to take a break and I'll do part B soon. See you.